In this video, we're going to learn how to use Simul8 software to construct a production line model in simulation. As usual, let's first go to File and Preference and Distance and make sure we set all the travel times to 0. Then we can construct the simulation model. Let's assume we're going to create a 5 machine line. We'll start with start point, and since I'm going to create a production line model with unlimited arrival of raw parts, I'm going to follow the start point with server. I'm going to delete this clock space. Save state, second server, third, fourth, fifth, and D. Okay. So now I have 5 servers, 4 buffers, start point, and an end point in the simulation. Next, I need to enter all the parameters. For instance, for the start point, as we mentioned, instead of having certain interarrival time and distribution, we're going to check this unlimited arrival. And you can see as soon as I do this, the interarrival time box becomes grayed out, so it becomes not active anymore. Click OK. And then for all the activities, all the servers, I'm going to bring out the activity, the property window. We're going to use fixed cycle time. Let's assume cycle time is 1 minute. And to enter the reliability characteristics, I'm going to go to efficiency. And as I mentioned in the PowerPoint, click on detail. This allows me to enter time between breakdowns and time to repair. And I'm going to do this one by one. So click on the time between breakdowns. And here, let's assume the average uptime, the uptime is follows the exponential distribution. And let's assume I have the average uptime being 20 minutes. And here, if you move your mouse on top of only count visit time, it tells you check this to only account for actual working time, not waiting time also, on calculating the time of the next downtime. In other words, if you check this box, you're looking at operation-dependent failure. If you leave this unchecked, then this will be the time-dependent failure. So for simplicity, in this module, we're going to use time-dependent failure. So we'll leave this box unchecked. Click OK. Go to time to repair. I'm going to choose again exponential distribution. And the average downtime, mean time to repair, I'm going to put 5 minutes. So 20 minutes average uptime, 5 minutes average downtime. The efficiency is 20 divided by 25, being 80%. Click OK to finish this, and then click OK. And now repeat this for all the servers, for all the machines. Fixed cycle time 1 minute. Efficiency detailed, time per time. Okay, it's 20 minutes on average, being exponential. Time to repair. Exponential distribution. 5 minutes. Third. And again. Fifth. 1 minute. Efficiency. Detail. 20 minutes. Exponential 5 minutes. Two more to go. Do it in fourth. Fifth. 1 minute. Efficiency. Detail. Time to breakdowns. 20. Time to repair. Choose exponential. And then 5. Okay, this last one. Fixed distribution. 1 minute. Of efficiency. Detail. Time between breakdowns. Choose 200. Time to repair. Exponential. 5 minutes. And that's it. So we're done with setting up the machines. Now, next thing to do is set up the buffer parameters. Instead of infinite capacity, let's use capacity of the buffer equal to 5 parts. Since the cycle time of each machine is 1 minute, average downtime is 5 minutes, so during one downtime on average, a machine can produce 5 parts. So we have all the buffers equal to 1 average downtime. Although we can evaluate, of course, the buffer capacity in terms of how many parts, but in production line analysis, it's usually good to know how many downtime or how many average downtimes each buffer capacity is equivalent to. This can help you quantify the protection capability of the buffers. Now we're done with the buffers. You can always go to the results manager and see what are the KPIs that are currently in there. And we can add a number of things of our interest. For instance, for the start point, as we mentioned, the number of items entered, jobs entered is important. But of course, we can obtain that in the endpoint, where you can gain the number of jobs completed. For queues, the number of things of interest to know will be the fraction of times, and that's usually available. Sorry, that's usually available in the activities, which, as we can see, the percentage time is waiting, meaning start, working time, blockage time, stop means downtime, and so on. So for these to happen, let's go to these activities and make sure we add waiting time, working time, block time, and stop time within downtime. And we can pull up the pie chart. And for the second one, we'll do the same. We'll add starvation time, which is waiting, working time, blockage time, and downtime. We'll also bring out its activity, the pie chart. Number 3, let's repeat the same. Waiting time, working time, blockage time, and right-clicking on these numbers to add those into the results manager. Almost done, 2 to go. So active number 4, starvation, working, blockage, and downtime. And same drill, add working, click on the utilization pie chart. This will give you the pie chart as we have Simul8 first. It will show when the simulation is done. Okay. Now we should also want to know the buffers. So we're going to add the average queue length, which will be our work in process, average queue sizes for all 4 of them. Since we have 5 machines, we have 4 in process buffers. Second, third queue, average queue size, and the last one. Now all performance indices are added. We want to go to clock properties, where we can set up the warm-up period and the results collection period. Let me use 20,000 as the warm-up period. Results collection period. Let me choose the simulation time unit. And let me use version 200,000. Or maybe just 100,000 minutes. So the reason of doing that is such that we can calculate the long-term or steady-state performance. And then I'll set up trials. As usual, I'll do 20 trials. Apply. Check all things. I can still do the random sampling. Check that I'll change the random number on every restart. Click OK. Back to home. And everything's all set. I can run trial. So this completes the model building. And I'll run and see how the simulation data turns out. As the trials are running, you can see the screen will be shining, and you can actually get a peek of what the pie chart will look like. Okay. While we're waiting, we can think about, well, this is the serial line with 5 machines, and I have all the machines having identical parameters. They have the same average uptime, same average downtime, same distributions for uptime and downtime, same processing time, and all buffers are also the same. They have the same capacity. So this one is symmetric from incoming to the outgoing direction. It'll be interesting to see if this symmetric configuration of system parameters will give us an interesting property. And we can see this in a minute. Now first, let's look at the results manager. Which collects a certain amount of data. If we're looking at the average time in the system, which is 24 minutes, and keep in mind that the processing time at each machine is 1 minute, and total process time will be 5 minutes. That means about 20 minutes is spent just by waiting in the buffer. Should have collected the number of jobs completed, but probably were able to add them. But by looking at the data here, we know, well, out of 100,000 time units or minutes, I'm able to produce 50,000 jobs. So by dividing the total number of jobs into the total observation time, I know the average throughput is 0.57 jobs per minute. All right? Now, keep in mind that since the cycle time of each machine is 1 job per minute, or 1 minute being the cycle time, we're looking at 57% of the process or the nominal capacity of all machines being utilized. That indicates there could be a lot of waste or idling that has occurred in this current system. So we just add that work completed into the results manager. So next time I run it, I'll be able to see it. Now, it would be interesting to also have a look at the results manager that we have for all the machines, the waiting time being starvation, working, blockage, and downtime. Now, all machines, as we set up, have 80% of efficiencies, 20 minutes average uptime, 5 minutes average downtime. So the downtime should be about 20%. As we can see, first machine, about 20%, 20%, 20%, 20%, and 20%. So this is an indication that the downtime, uptime, and downtime efficiency are set up correctly. Now, it's also interesting to see the utilization rate, or the percentage of time the machine is working. 57%, 57%, 57%, 57%, 57.1%. This is actually equal to what? Equal to the throughput rate, which is, as we calculated earlier, (57.1%) or 0.5710 jobs per hour per minute. And this is not just a coincidence. This is all meant to be. Since the percentage of time working divided by the cycle time 1 minute should give us the throughput rate. Exactly what we're expecting based on what we have discussed in class. Other things of interest to see is if we look at the starvation and blockage probabilities. For instance, we look at the probability of blockage of activity 1, machine number 1, about 22.6%. And if we look at the starvation probability of the last machine, very similar, 20.4%, 22.4%, almost the same. Now for the second machine, starvation 6.5%, second to last machine, blockage 6.6%, again very similar. Second machine, the blockage 16%, Second to last machine, fourth machine, the starvation, 16%. For the middle machine, activity number 3, machine number 3, waiting time or starvation time, 11%. Block time, also about 11%. It means that this symmetric thing not only applies to the parameters, but also applies to the system performance. And through the pie chart, we can even see this. 22%, 22%, 6%, 6%, 16% block time, 16% starvation time. And here we have 10%, 11%, 11% waiting and blockage for the middle machine. This phenomenon is what we call reversibility. When you have a perfect symmetric line, you have perfectly symmetric, or in this case, numerically, practically symmetric phenomenon of the performance metrics. And this not only applies to the machine performance. If we look at the work in process, which will be the average queue size, if we add up the work in process of the first buffer and the work in process of the last buffer, 3.44 plus 1.58, this is equal to 5.02. And remember, 5 is the capacity of the buffer. If we check the middle two buffers, which are symmetric in symmetric positions, 2.78 plus 2.23 is equal to 5.01, again approximately equal to the capacity of the buffer. This is the reversibility in terms of the buffer capacity. And tells us the story that because of the symmetric thing, it is important to understand that if you have a perfectly symmetric system, the front of the line and the end of the line will have equal impact. And usually the one towards the middle has to be or has to receive more attention, since it experiences more disturbances from the upstream down events and the downstream down events, or machine failures. Now, with all these numbers, as we mentioned in class, we will be able to calculate, for instance, the total energy power consumption of a production line like this. If we know the power consumption characteristics for the machines during each particular scenarios, stop, downtime, uptime, blockage, or starvation. And this enables us to do some quantitative analysis of not only the productivity, which is through the number of items produced, but also the amount of energy consumed. And by changing the parameters, play around with this, we'll be able to experiment how you can improve the productivity or improve the energy performance of the system through all these numbers. Now, it's worth noting that if we go to each of these activity measures buffers or activity, it's possible to indicate the carbon footprint in the simulation. However, the carbon footprint setup in Simul8 is not an ideal way to do this. This only gives you the capability to put fixed footprint, kind of a constant power consumption over time, and the footprint or the power consumption per time unit and per job produced. Now, since we have the information about all these time periods for each machine, it provides a more comprehensive way to calculate the energy performance. Okay, this concludes the explanation of how to use Simul8 to build a simulation model for a serial production line. This Simul8 file will be uploaded onto Husky City for a reference, and if you modify the for all the homework assignment problems you're going to work on.